So good morning, guys. I hope you're having a good day, at least looking forward to the weekend and de-stressing a little bit. I know it's been a hectic week, and I think the seniors mentioned yesterday that presentations are due today, so I wish you all the best of luck in that, as well as on design presentations next week. But you guys are almost through, so just, give it your best shot, and I'm sure you guys will all do really well. So for here today in class, we're going to be continuing our discussion on boiling and condensation, talking a little bit about equations in boiling, working a couple examples, probably one or two, if that, and then talking about condensation. One thing I do want to mention, I am almost finished with your exams. I'm hoping to get all that out today and then let you guys look it over the weekend. If you have questions, comments, concerns about grades, we can kind of talk, hash them out, make sure that the data I have is the data that you see. We kind of agree in terms of where those scores are falling. And if you do have any questions regarding that, like I said, I recommend probably sooner rather than later getting to me, because it's a lot easier for me to work with you before finals week to try to deal with any issues or discrepancies than during finals week. It's just a lot. I appreciate it more definitely than having the one person show up the day after finals and give me a laundry list of things that we need to figure out. I'm also going to push back the homework due dates to probably next Thursday, just because there's a reasonable chance we might not get finished with this information today. And I know we didn't finish yesterday on this section, so I'm going to be pushing back that stuff to next Tuesday, or excuse me, next Thursday. So you'll have a little bit more time, and I'm sure you guys could use it. We're getting down to the wire. The energy and to kind of get through is probably a little low, so I like to give you guys a little more wiggle room. Are there any questions before we jump in to today, or any questions you have from Wednesday? I don't know why I did that. All right, if not, all right, so on Wednesday we were talking about boiling heat transfer. And we stated that we had several boiling regimes, which are highly dependent, or where heat flux is highly dependent on delta T excess. And so our initial stage was natural convection. Then we had nucleate boiling. And after nucleate, if we exceed the maximum critical heat flux, we enter film boiling, where we have the potential for burnout. And then we have transition boiling. And we talked a little bit last time about the boiling curve and how in this curve we kind of move up, moving from natural convection to nucleate boiling, where the bubbles don't escape. Then the bubbles start to escape. We get to our maximum heat flux, and then we go all the way into film boiling, where we have potential burnout. So today, we're going to jump in and start talking about calculations. associated with boiling heat transfer. And so for natural convection boiling, we typically rely on Newton's law of cooling and heat transfer equations, or H equations, associated with natural convection. We don't really talk about them and we don't really jump into those calculations, primarily because they're not efficient. And if we're dealing in a process, we want our system to be efficient. And so what that means is 9 times out of 10, we're going to be operating in the nucleate boiling regime. And the nucleate boiler regime is unique in that our heat flux is going to be dependent on the ability of our surface to generate nucleation sites. And the issue with this kind of idea is that it's a little difficult to predict. And thus, correlations or empirical correlations are used. And so, with this in mind, we can calculate the heat flux in nucleate boiling as the viscosity of our liquid times our enthalpy of vaporization times the quantity of gravity times the relative difference in densities between our liquid and vapor over the surface tension of our liquid to the 1/2 power times the heat capacity of our liquid times the surface temperature minus the saturation temperature, or our delta T excess, over a constant C sub SF, which I'll get to in a second, times our lambda times the Prandtl number of our liquid to the n power cubed.
Is that supposed to be mu liquid, then
Yes.
rho liquid and rho vapor? Okay.
Yes. And so CSF and N are measures of nucleation ability. And just to make sure everyone's on the same page, do you guys kind of understand what I mean by nucleation sites?
It's the sites where the bubbles start to form.
Yes, where the bubbles form. I only asked, I had questions on that yesterday. All right. So with that in mind, the question is, how do we find CS and CF? Well, they're empirical, which means you have to do a little digging and research to identify them. Some examples, where you can kind of see here, and it's important to identify that they're functions of both essentially the fluid and the surface, right? Because boiling happens at that interface. CSF and N take into account both substances. And so you can see kind of water with various systems and then pentane with various surfaces.
And for like, what kind of controls it? Just out of curiosity, is it just like atomic interactions between your fluids, or how? What makes one thing nucleate better with one metal versus another?
That's a really good question. We can do a really kind of brief deep dive on that if you'd like. So propensity for nucleation, well, it's just weird. If you look at that interface, kind of at that, microscopic level, the surface is going to have some degree of roughness. And nucleation is a measure, or requires both a sufficiently rough surface such that the liquid interfacing at that, point has a little bit greater than average surface area, meaning there's going to be greater than average heat transfer at that point. And so spots that are considerably quote unquote rough, that have greater than average surface area, are going to exist as nucleation sites. At the same time, you have to consider what's known as wettability of that surface and the liquid. If you can, kind of imagine like something that interacts with water in a way that the water doesn't want to wet it very well. So something like a Teflon, you're not going to get the best type of interaction because that liquid doesn't want to come into contact with that surface. And so if you have a high degree of wettability of the surface by the fluid, you're going to get the greater propensity for nucleation as well as boiling. Now in surfaces like that, you can overcome that very easily with what's known as boiling chips. Have you guys heard of boiling chips? And they're just
Yes.
essentially small pieces of like essentially really porous rough rock, such that these rocks can get really hot and basically just like the surface at the bottom, but they end up being really porous, such that you have this kind of rock that's really porous here, rock that's really porous here, rock that's really porous here. And as the liquid wets that, essentially the pores, the heat can come in from all directions, which makes it excellent nucleation sites, which is why they're called boiling chips, because they kind of greatly enhance a boiling ability of most liquids because of that fact that you have a really highly porous, rough structure. And so things that you might consider mechanically smooth, but you want to have boiling occur. That's why so in some instances you can consider using boiling rocks, boiling chips, whatever they call them, in that kind of surface. So that's kind of essentially how and why the solid fluid interaction is important, because as we said on Wednesday, enthalpies of vaporization are really high, which means you need a lot of energy put into those molecules to get them to vaporize. And so the greater the ability to do that, i.e. the more surface area that you have in contact with those molecules, the later likelihood you're going to see those bubbles form. So long answer, but I think it was a good deep dive. Hopefully it answered your question. So in addition to looking at the general nucleation, heat flux, We can also solve for both the maximum or critical heat flux, Qmax, which is equal to 0.09 times the density of the vapor, times our enthalpy of vaporization, times our surface tension sigma, times gravity, times our relative density, density of the liquid minus density of the vapor, over density of the liquid plus density of the vapor, squared to the 1/4.
What is sigma?
The surface tension of the liquid.
And can we find that value in an appendix or a table somewhere in the book?
Oh, hold on. I think this is Q min. John, you were asking about sigma? Was that what you were asking about?
Yeah.
Sigma is something that you look up. It's an intrinsic property of the liquid at a given temperature and pressure. For the most part, Dr. Rowe might argue a little bit more about that, but he's not here. Qmax, if I look at the right part of my notes, is another constant, CCR, I believe, times our enthalpy of vaporization, times our surface tension, times gravity, times the density of our vapor squared, times the density of our liquid minus the density of our vapor to the 1/4. Sorry for the confusion.
That's CCR, that first term. Is that right?
Yes. Yeah, they're typically pretty strong functions of temperature for surface tension. For CCR, it's another empirical constant, which we obtain based off of the geometry of our heating element. And so this line here is illustrating that fact that depending on the geometry of your heater and the characteristic length that you have of that heater, you can calculate this dimensionalized parameter for that characteristic length, and then based on that range, you can identify your constant.
And just to confirm, is G the gravitational constant, or is it going to be mass velocity here?
It's going to be the gravitational constant. And the last heat flux we may be interested in is finding the heat flux in film boiling, which is another constant, C sub film times a whole big mess of things, G, gravitational constant, times the thermal conductivity in our vapor, times the density of our vapor, times the relative difference between the density of our liquid and vapor, times our enthalpy of vaporization, plus 0.4 times the heat capacity of our vapor times delta T excess, Ts minus T sat, all divided by viscosity of our vapor phase times our delta T excess over times diameter all to the 1/4 times delta T excess. And I'll give you guys a second to jot these things down.
What's that D value?
The D value
Yes.
is the essentially heating element's diameter, assuming it's a cylinder or a sphere, because this equation is technically for cylinders or spheres. 9 times out of 10, it's going to be a cylinder. And C film is going to be approximately 0.62 for cylinders, or horizontal cylinders, I should say, and 0.67 for spheres.
Will we not look at vertical cylinders?
Not really for this, as it gets a little complicated. We'll see some of that when we look at condensation, but the gravity term is important in this case, and the orientation is as well, because with these temperature and phase fluctuations that we're seeing, right, going from a liquid to vapor, these systems are going to move. And so the issue that happens when you have, let's say, a vertical cylinder is that the vaporization at the bottom interferes with the vaporization at the top. And there's no real good way to model that. Well, we see that the same thing happening when we talk about condensation. If we've got like a vertical plate, right, as it condenses, going from a vapor to a liquid, the liquid's gonna move down with gravity, and in that case, it's going to influence the bottom's plate ability to condense vapor. All right. So those are the key equations that we really look at, and boiling heat transfer. They kind of give you the impression of alphabet soup, as I like to call it. But the goodish news is that there isn't a whole lot of, I would say, deep application or reasoning behind some of the equations. It's mainly just identification of the proper values of the liquid and vapor, determining your constants, and then solving for the heat transfer. It's not like fluids where you have to have deep philosophical debates about what to do before you actually do calculations. These are a lot more straightforward. The calculations are just complex. And so I definitely recommend for boiling and condensation heat transfer, as these equations look a little messy, try to do calculations in metric units. if at all possible. It just makes not having to worry about G sub Z and things like that a lot better. So with that, let's take a look at an example where I have water in a tank going to be boiled at sea level by a 1 centimeter diameter nickel plated heating element, assuming it's a cylinder. Estimate the maximum heat flux that can be attained in the nucleate boiling regime and the surface temperature of the heater in this case. Okay, so let's look at this system. This example is going to be boiling water. And one of the important things to note is that we want to identify the properties at the liquid saturation temperature. So if this is just standard water at, 1 atmospheres, we're looking for water properties at Tsat, which is approximately 100 degrees Celsius. So for this problem with water at 100 degrees, our density is going to be approximately 958 kilograms per cubic meter. The density of our vapor is going to be approximately 0.6 kilograms per cubic meter. Our enthalpy of vaporization is going to be 2,257,000 per million joules per kilogram Kelvin. The diameter that we had of our element was 1 centimeter or 0.01 meters. The Prandtl number for water at 100 C is approximately 1.75. The heat capacity is 4217 joules per kilogram Kelvin. And the viscosity of our liquid is approximately 0.28 Pascal seconds, I believe. Actually, that seems pretty high. It should be 0.28 centipoise. All right. And what am I missing? I'm missing surface tension. Surface tension here is going to be 0.0589 newtons per meter. And so this is just, lots of research or Googling. Reputable references. If I give you a problem like this on the final, which I just might, I would most likely give you all of this except for, no, I'd probably just give it all. Which is why people like these kind of problems on the final. So if we're looking for the maximum critical heat flux, we know Q max is equal to CCR lambda times sigma G rho V squared rho L minus rho V to the 1/4. So we need to find CCR. So in this problem, switching over to the slides, if we assume it's a horizontal cylinder, and it's a small horizontal cylinder, we need to identify L star, where L star is equal to L times G times rho L minus rho V over sigma to the 1/2. And then based on L star, we can identify where our cylinder values fall. So in this system, we can calculate L star. So L star is going to be equal to L, which is our characteristic length or our radius, or 0.005 meters, times gravity, 9.81 meters per second, times the density of our liquid, 958 kilograms per cubic meter, minus density of our vapor, 0.6 kilograms per cubic meter, over our surface tension, which is sigma, or 0.0589 newtons per meter, all to the 1/2 power. So what do we get from this? So from this, I got about an L star of approximately 2, which if we jump back to our example, our table, an L star greater than 1.2 is considered a large horizontal cylinder, in fact, with a CCR value of 0.12. So that means CCR is equal to 0.12. And thus Q max is equal to 0.12 times our enthalpy of vaporization, 2257. So let's just say times 10 to the third joules per kilogram Kelvin, times our surface tension of 0.0589 newtons per meter, times gravity, 9.81 meters per second squared, times the density of our vapor squared, or 0.6 kilograms per cubic meter squared. I'll zoom out so you can see easier. Times the difference of our densities, 958 minus 0.6 kilograms per cubic meter, all to the 1/4 power. So we do this, and I get 1.02 times 10 to the 6th watts per meter squared. Any questions on this so far? All right, if not, we can keep going. The next part of the question asks, what is the surface temperature of the heater at the maximum critical heat flux? Well, to find that, what we need to do is find our delta T excess. And since we're in the nucleate boiling regime, we can say Q max is equal to Qn, which is equal to mu L lambda G rho L minus rho V over sigma to the 1/2 times CPL TS minus TSAT divided by CSF lambda Prandtl number to the L to the N cubed. And this is going to be equal to that 1.02 times 10 to the 6 watts per meter squared. And so we have all the values. The only values we don't have is C as F and N. So to find that, we go to our table. In this case, we have water in a nickel-plated element. So for water and nickel, CSF is 0.006 and N is 1. And so to set up the problem, I would say 1.02 times 10 to the 6 watts per square meter is equal to the viscosity, or 2.8 times 10 to the minus 4 Pascal seconds times 2.257 times 10 to the 3rd joules per kilogram Kelvin times everything else, 9.81 meters per second squared, 958 kilograms per cubic meter, minus 0.6 kilograms per cubic meter. I'm going to have to zoom out a lot of this. Divided by the surface tension of 0.0589 newtons per meter to the 1/2 times the quantity of the heat capacity, which is 4217 joules per kilogram Kelvin, times our delta TXS. Makes it a little easier to solve if you just leave it as one term. Over our CSF, which is 0.006, times our lambda, 2257, times 10 to the 3rd, joules per kilogram Kelvin, times our Prandtl number, which we had as 1.75. It's the N, or just 1 cubed. So it's messy, but it's just one equation, one unknown. If we do this and plug it in, we get a delta TXS of about 19 degrees C, which implies our T surface temperature is 119 degrees Celsius. Any questions on this example? You guys following along okay? Perfect. Thank you for the feedback. I appreciate it. All right. So with
Can you
this,
go back up for a second?
of course,
Thank you.
you still copying down?
Yeah, thank you.
No problem, I understand. So with this, I want to shift gears and start talking a little bit about condensation. Once again, we'll probably not get very far into it, but still something I want to get into. So with condensation, we have essentially the temperature of a vapor falling below the temperature of saturation, or the saturation temperature. Or I would actually, that's not the best way, approaching the saturation temperature. And this is accomplished by bringing that vapor into contact with a solid surface whose temperature or Ts, once again, is well below the saturation temperature of the vapor. Though I will say, unlike boiling, this can occur when in contact with other liquids or gases, or even other gases. A good example of this would be fog, the condensation of very, very small droplets suspended in air. Now, while things like fog is all well and good, if we're engineers, we want efficient ways to condense liquids for our processes of interest. And so we have two distinct forms of condensation to consider. The first one being film condensation. And the second being what's known as dropwise condensation. And so in film condensation, the liquid that forms, or condensate, wets the surface and forms a liquid film of a given thickness. Which we categorize as a delta. And this differs from dropwise condensation, where in this case, we're condensing vapor. We'll form droplets instead of a film. And so what that means is the droplets form and slough off of the surface before a continuous film forms. So which of these two forms of heat transfer do we expect to be considered desirable in an engineering application?
Dropwise condensation.
All right, I got a vote for dropwise. What do you guys agree? Are you team dropwise? I saw some yeses. I got anybody for team film? Nobody for team film? Everybody's for team dropwise?
Film seems like it'd be better to me because it's like uniform.
It's
Okay.
uniform.
I don't know.
I got everybody's falling on the dropwise. Holly's on the fence.
I feel like dropwise would be better because film is the maximum, and at that point you don't have control. You can't get more. It's hard to turn it down, so you get less. Dropwise, you can control it more easily.
Okay. I like that. It's good. The real answer is not as black and white as I'm originally painting it out. And I will say this because you guys are right on the money when it comes to interpretation of both of these systems. So for film condensation, that liquid film is going to provide or presents a resistance to heat transfer. Similarly, as we saw in film boiling, right? When that vapor was in the way, now the solid surface isn't interacting with the liquid it's trying to boil because there's vapor in the way. And for film condensation, we have liquid in the way of the vapor that we're trying to condense, right? And so as the vapor is condensing, it forms its own resistive layer that counteracts that, desire to get that vapor to condense. And dropwise, we don't have that issue. And so what we find is that, on average, dropwise condensation in that the heat fluxes we experience in dropwise condensation are about 5 to 10 times higher than what we see in heat fluxes in film condensation. Now there's a problem in that. And the problem is if you have really good performance in your system, your dropwise condensation system will very quickly become a film condensation system. Meaning is if you're operating efficiently, your systems to a certain degree is going to be self-regulating. Meaning if I have a process and I'm wanting to condense a chemical of interest, but in an efficient manner where my mass flow rate or in my condensation rate is going to be appreciably high. To operate in a true dropwise fashion, that's going to require a large exchanger. And so primarily because you need to have room for those droplets to form. And 9 times out of 10, area is money. And so what happens is very quickly, something that's operating dropwise will become a film system. And so that liquid film will form. And thus, what we find is for engineering applications, our systems are analyzed assuming film condensation occurs. Because once again, if you're doing your job right, that vapor should be condensing at a high rate. And if the vapor's condensing at a high rate, you're not going to have room for dropwise condensation to exist. That resistance layer is going to build up. And it's best to design your system for that resistance. Does that make sense? Is that clear? Any points of discussion that I can kind of clarify?
Yes.
That's a good answer, Blake. You're starting to sound like me.
All I could think of was honestly the throttled flow, and when you were talking about how we don't want it to its max velocity, we want it to be able to control it.
Yeah.
For
Yeah,
choke
that's
flow.
yeah, it's kind of like that in this system, right? Is it self-regulates, right? You get good condensation, and then the more condensate you have form, the greater the thickness of that film, and the greater the thickness of the film, your heat transfer will decrease. And so, if our metric is, how many tons per hour are we getting in condensate, that's going to be a self-regulating system. And so that's kind of the issue when it comes to film condensation, is if you're doing it right, the system will make itself, essentially make more work for you. And so even though dropwise is technically more efficient, you have a higher heat transfer, in terms of productivity, you're not making enough condensate. And if you were, it wouldn't be dropwise.
That makes sense.
Yeah. It's kind of one of those, you're in trouble either way, but at the end of the day, you need to be operating in that film condensate regime.
Yeah.
Now, I think I had another question, but the chat doesn't want to show up for me. All right, hey, see, Walker's got it. It depends. That's the answer to every question. Though I wouldn't recommend putting it on the final. Now you guys are learning. All right, I think that's all the time we have today. We'll go ahead and wrap this up on Monday, and I think we might have just enough time in this semester to maybe talk about some fun, crazy things in radiation heat transfer. So I think module 12 will be the last module. So hooray, I'm sure you guys are so broken up about that. And it'll be a small one for radiation. One thing, I haven't posted a quiz or a synthesis assignment yet. I may skip the synthesis assignment, and if I put something, it might just be like a 1 or 2 question survey that's just kind of freebie points. I will post a quiz probably by the end of the day. I usually don't worry too much about posting them late because I kind of want you to do those last anyways.
So that'll be due Thursday also?
Yes, that will all be due Thursday. So you guys will have plenty of time to do it. But like I said, I know you guys had other exams this week. The seniors are about to get chewed out politely by other faculty. And so I try when I can to consider my class as it influences and exists in the realm of other classes, unlike other faculty. But that's how it is. All right. Take care, guys. Have a great day and a great weekend.
Thank you, Dr. Lopez.
Thank you.
Bye,
Thanks,
guys.
Dr. Lopez.